Okay, shall we start right now? Okay, so next and last speaker today is Yaron Ostrover from Tel Aviv University. We speak about on symplectic radii of LP products.
Thank you very much. I would like first to thank the organizers for the invitation to speak here. I'm going to talk about certain computations in symplectic topology, and most of what I'm going to talk about is a joint work with Vinicius Ramos. And if time permits, I will try to mention some other related projects. And please feel free to stop me at any point if you have questions. So the starting point of the talk is the symplectic embedding problem that was already mentioned in this conference. It's very easy to state. We have two symplectic manifolds, and we want to symplectically embed one into the other. Now, of course, in such a general setting, this is a transcendental question. Extremely difficult question, but even though that it's extremely difficult, it serves as a very strong force, strong positive force in symplectic topology and Hamiltonian dynamics, and many tools that have been introduced to the field can be used to tackle the question of symplectic embeddings. And the first, historically, first example is the theory of Gromov's theory of pseudo-holomorphic curves, which, among many other things, can be used to prove the famous non-squeezing theorem, embedding of a symplectic embedding of a ball inside a cylinder. Yesterday, in the beautiful talk by Dusa Megdaf, Megdaf mentioned one example that I want to remind you, and this goes under the name the Megdaf-Schlenk infinite Fibonacci stairs, and this is the question of embedding an ellipsoid in C2 into a ball. So I want to refer to this question as the symplectic outer radius of the ellipsoid in C2. So this is the ellipsoid. We have two parameters, A and B. We can normalize one of them and think about this as a one-parameter family of examples of ellipsoids. And Megdaf and Schlenk studied the following function. So for any given, say, A bigger than 1, we are interested in the smallest ball that one can symplectically embed the ellipsoid inside. Now, there is a natural obstruction coming from volume. This is the square root of A. And Megdaf and Schlenk managed to compute this function. Now, I'm not going to be very precise. I'm just going to show you the following picture. So when A is very large, essentially there is only the volume obstruction. So there is what we call a symplectic flexibility. There are no other obstructions to this embedding. But for relatively small values of A, we see that the function is piecewise linear, and there are infinitely many jumps, and the jumping points are somehow closely related with the Fibonacci number, as Megdaf explained in her talk yesterday. So we see that even in a very relatively simple example, the embedding of an ellipsoid into a ball, the behavior is quite complicated. So we see both symplectic flexibility, like in the points here, that the volume is the only obstructions. And there are these points here, for example, that we have what we call symplectic rigidity, that although there is no volume obstruction, there are certain symplectic topological obstruction for this embedding. Okay, so this is the question that we want to consider, and more generally, we have, say, an open set in the classical phase space, and we are trying to compute the symplectic inner radius of the set and the symplectic outer radius of the set. So this is what we would like to study. Now, I should say that so I'm going back for a second to the previous example. Again, Megdaf mentioned in her talk that in higher dimension, we already don't know to completely analyze the embedding of ellipsoids. So there is, in dimension 4, we have certain tools that one can use to answer these type of questions. So as a first step, we can try first to compute or look at this question only in dimension 4. But even in dimension 4, I would like to say that we are very far from being able to answer this question. And my favorite example is a rotated cube. So take a cube in R4, look at the rotation of the cube. Now, of course, the rotation not symplectic, not unitary, and try to understand the inner and outer radius of this rotated cube. And of course, the reason why this is a difficult question is that I would say almost all of our tools to get, say, obstructions for symplectic embeddings come from some homology theory that is based on the rel dynamics on the boundary. So without a very or reasonably good understanding of the rel dynamics on the boundary, it's very difficult to, say, compute numerical invariants or capacities that can serve as obstructions for these type of questions. Okay, so the question, my point is that the symplectic embedding question, even in R4, even in very, very simple examples, is in some sense out of reach. And most of the examples that were studied so far in this context are ellipsoids or polydiscs, where we have a very good understanding of the dynamics on the boundary. And what's kind of the question that I would like to pose is which class of domains, suppose we do want to answer this question of the computing the symplectic inner and outer radii, which class of domains we should look at, or which class of domains are is natural to study. Now, of course, everyone can interpret the word natural here as he wish. So for me, natural means that it should be, say, maybe related to Hamiltonian dynamics in one way or the other. And on the other hand, that you would have enough control on the dynamics so that we would be able to say something about this event. And the first thing that I would like to do in this talk is to suggest kind of a candidate for this class of domains. And the class that I want to consider is based on the fact that the classical phase space is the sum of two Lagrangian subspaces. So what do I mean by that? I'm consider the natural splitting of R to N, saying X and Y coordinates, or P and Q coordinates, if you wish. And I'm going to choose domains in these two Lagrangian subspaces. Now, in this talk, I'm going to consider only nice, symmetric, convex domains. This is already interesting enough for the symplectic embedding questions. So I'm going to think about these Lagrangian subspaces as normed spaces. So each one of them is equipped with a norm, and the unit ball of this norm is some symmetric convex body. So I have this convex domain in the X space and another convex domain in the Y space. And now I want to generate a domain inside the phase space itself. And there are many ways to do that. And kind of the classical one is to look at the LP sum or the P sum of these two normed spaces. So here is the picture. And remember, you have to keep in mind that this is a Lagrangian splitting, right? So it's R2N with a Lagrangian splitting. So for P equals infinity, we just have the Lagrangian product of these two convex domains. For P equals 1, we have the following thing. So we have, say, you have an ellipsoid in the X space and another ellipsoid here. And what we look at some sort of a convex hull of these two ellipsoids. And a particular interesting example is the case of P equals 2, because the two sum of two ellipsoid is an ellipsoid, right? So if you take an ellipsoid here and another ellipsoid here, then the two sum is going to be an ellipsoid. So this is the class of domains that we want to consider. And well, in some sense, this is motivated by Hamiltonian dynamics in the sense that you can consider Hamiltonian functions of say the classical harmonic oscillator. You can think about the classical harmonic oscillator as the two sum of two balls or two disks.
So do you mean that you're taking the unit ball with respect to this XYP norm?
Yes, I mean, in general, I can take any, say, convex body in a pair of convex bodies in this Lagrangian splitting and look at the P convex combination of these two convex bodies.
Okay.
Okay. Okay. So again, if you kind of going back to this example of the harmonic oscillator, one way to think about the harmonic oscillator is the two sum of a ball in the X space and another ball in the Y space. And what we want to understand is how changing P, so we can think about this as a one-parameter family of example, and I will try to convince you that we have certain tools, in some cases at least, to try to study the embedding question in this setting. And what we want to understand first is how, say, if we think about this as a one-parameter family, how the dynamics is changing by changing the variable P. And the first example, the most natural example that I want to consider is indeed the case of the LP sum of two disks. So we take, say in R4, we take two, so in R4, we take two disks, and I should emphasize that what we are doing, we are taking this Lagrangian splitting. So it's the P sum of two disks with respect to a Lagrangian splitting. And we want to study the symplectic embedding question in this particular example. So I can start with describing what can be said about this particular example. And using the theory of integrable Hamiltonian systems, we can prove the following thing. So XP is what I just said, is this P sum of two disks. And again, this theorem is only in R4, because I will explain later on that the tools that we are using are based on ECH capacities and other techniques. We can use them only in R4. And we want to compute the symplectic inner radius and the symplectic outer radius in this case, and especially to understand how it depends on the parameter P. So here is the answer. The inner radius can be computed explicitly. Here are the two formulas. I mean, there is a certain phase transition at P equals 2. And the outer radius, slightly more difficult to compute, can also be computed explicitly. But here, I mean, it's the formulas that we get for the outer radius are quite complicated, especially for values of P which are bigger than 9/2. But the point is that both the inner radius and the outer radius, the symplectic inner and outer radius, in this example can be computed explicitly. Okay, yes. Explicit computation. Now, I want to emphasize that, and I will try to explain where it comes from, but this phase transition at P equals 2 is in some sense not very surprising. I mean, I can explain where it comes from. But note that here we have another some sort of a phase transition at P equals to 9/2. And I have to say that I don't completely understand this phenomenon. I mean, from the Hamiltonian point of view, I mean, from the Hamiltonian dynamics point of view, I don't see any particular meaning to this particular value, 9/2. I mean, I will explain how it enters the proof, but I have to say that I don't completely understand why this phase transition appears from the Hamiltonian dynamics point of view.
May I ask a question?
Of course.
Is there a meaning to the fact that for the inner radius you have something, I mean, 2 pi 1/4 blah, and then the other formula, and then it's just switched around for the outer radius?
Well, okay. So first, as I said before, they switched around, but only for P values between 2 and this strange 9/2. Yeah, but I mean, I will explain in a second how did we end up with these numbers, and yeah. But, I mean, a priori, just by kind of thinking about the Hamiltonian dynamics, you don't see immediately how to get this number. But in a second, I believe it will be.
There's also a question in the chat whether these two sums are symplectomorphic to toric domains.
Yes, this is the next thing that I want to say. So I want to relate this story to toric domains. Okay, this is the next thing that I want to say. Okay, but before that, I should say that the case P equals infinity, which corresponds to the case of the Lagrangian bi-disk, so just the product of two Lagrangian disks, was previously studied by Ramos, and it is closely related with billiard dynamics, and Ramos computed the inner radius, the outer radius, and also several embedding questions for this configuration of the Lagrangian product. And the formulas that we see here, of course, when we take P to infinity, they recover the formulas obtained by Ramos. Okay, so how did we get these formulas? And indeed, we use integrable Hamiltonian systems, so use the language of toric domain. So let me remind you what is a toric domain in C2. And of course, simple examples are the ellipsoid or cylinder, example of toric domains. And the point behind the proof is that this configuration, the P product of two Lagrangian disks, is symplectomorphic to either a concave or a convex toric domain. And now we are in a territory where we have lots of tools to investigate symplectic embedding questions. So we have both the ECH capacities that one can use for getting obstructions to embedding, and also some techniques that can be used in this particular case to construct embeddings. So the case of convex and concave toric domains is a very special case where there are lots of tools developed by many peoples that can be used to tackle symplectic embedding questions in these cases. Now, what is the toric image of this configuration? Well, it's quite complicated. I mean, again, it can be computed very precisely, but formulas are somewhat horrible. But of course, you can completely ignore the actual formulas here, but note that we see this phase transition at p equals 2. I mean, the toric image is convex or concave, depending whether p is between 1 and 2 and p is greater than 2. Okay, so the toric image changes when p crosses the value 2. And of course, for p equals 2, it's the 2 sum of 2 disks, which is just the ball. So we get the Euclidean ball in this case. Any questions about the theorem? Okay. So how do we prove this result? Well, sorry, before saying something about the proof, let me say a little bit more about the statement. So I want to introduce some notations. Okay, so suppose we have two subdomains in R4. So we say that the symplectic embedding question of x1 into x2 is rigid if one cannot do better than the inclusion. There is just nothing better that can be done other than the actual inclusion. We will use, and this is maybe not a very standard terminology, we will use the terminology torically rigid if after we switch to the toric picture, if there is kind of a symplectomorphism between these domains and toric domains, such that after looking at the toric image, we get that the embedding is rigid. Okay, so this is our definition of torically rigid. And we will say that the embedding question is non-rigid if neither 1 or 2. Okay, so this is the terminology that I want to use. And we can say a little bit more about the symplectic embedding problem. We know that in terms of the inner radius, the symplectic inner radius, we have rigidity between 1 and 2, and torically rigidity for every p that is greater than 1. So between 1 and 2, there is nothing that can be done other than the inclusion. Okay. And when we move to the toric picture, there is just nothing that can be done starting at p equals 1. This is for the inner radius, and the situation is somewhat more complicated for the outer radius. So here we have torically rigidity exactly for these values between 1 and 9/2. Between 2 and 9/2, we have just complete rigidity. And starting and passing this value of 9/2, we just lose this rigidity completely. So the embedding is non-rigid. So it's kind of a strange behavior of these embeddings as a function of P because of the behavior, the change of the change transition at this specific value of 9/2. So this was somehow unexpected. The phase transition at P equals 2 makes sense somehow, but this transition at 9/2 is something that I have to say I don't completely fully understand in terms of the dynamics, and it has to do with the embedding techniques that we use in this framework of embedding of convex/concave toric domains into convex/concave toric domains. So I'm not saying much about the machinery. I'm just saying that this is the source of this particular numerical value. Now, the proof goes through the fact that this system, the P sum of these two disks, is in some sense integrable Hamiltonian system. And we can use the Arnold-Youville theorem. So I'm not going to be super precise here, but the Arnold-Youville theorem tells us, roughly speaking, that when we have a integrable Hamiltonian system, then we can find this toric image of the domain. And so again, I don't want to be too formal here. I just want to say that using the Arnold-Youville theorem, one can get the toric image of the Hamiltonian dynamical system. And in the case of the P sum of two disks, there is two natural commuting Hamiltonian functions. So one is the generating Hamiltonian function, denoted here by HP, and the other one is the angular momentum. So these are the two commuting Hamiltonian functions, and one can apply, roughly speaking, the Arnold-Youville theorem to get a toric domain. But there are several technical issues here that I'm hiding. So first, there are regularity issues. I mean, these functions are not smooth enough to use the theorem as it is. And the second thing is that it is not enough for us to be able to answer the symplectic embedding question. It is not enough just to end up with a toric description of the body. It is important to get a toric picture which is convex or concave. Okay, and you have to work carefully, or to do the computations very carefully, so that you choose the right symplectic coordinates to look at this Hamiltonian dynamical system. But this is roughly where we get the toric image, and then we use the technology that I mentioned before to tackle the questions of symplectic embeddings. Okay. Any questions so far? Okay.
Yes. Can I ask a question?
Yes.
So you took the P product of two disks. Does this generalize if you take the unit disk of a norm and of a dual norm?
Okay. Yes. So the short answer is that for general convex bodies, I don't know the answer. I don't believe that in terms of Hamiltonian dynamics, that this configuration, the product of a norm and a dual norm, is always integrable. I mean, I somehow find it hard to believe that this is always the case. But of course, it's possible to have the toric picture without this integrability that I mentioned before. So I guess what I would like to say is that if you just look at the Lagrangian product or P sum of a domain and its dual, I don't think that it is an integrable Hamiltonian system, but there still is a possibility that it is a toric domain. I'm not sure if I answered your question. Or so this answered the question, or just?
Yes, it did answer the question. Thank you. Yes.
Oh, thanks. Yes. Yes. So of course, this is only one example, the P sum of two disks, and I still need to convince you why I believe that this is, in general, a natural class to consider. But before doing that, let me make a comment about the symplectic sum of convex bodies. So I'm changing now the setting. Instead of looking at the P sum of convex bodies with respect to a Lagrangian splitting, I'm going to consider the P sum of convex domains with respect to a symplectic splitting. Okay, they're completely different dynamical systems. Now, recall that when we have some symplectic capacity or some symplectic invariant, in many cases, we have the so-called product property, especially for normalized symplectic capacities. So the symplectic invariant of the product is the minimum between these two invariants. Now, for many well-known symplectic capacities and for, say, nice class of domains, this is known to be true. In general, of course, it's not clear when we should expect this property, but here we are dealing with convex domains in the phase space, so we definitely have, say, for certain normalized symplectic capacities, we have the product property. And we can ask what can be said about the product property when, instead of looking at products, we can look at P sums of domains. Okay, so again, it's important for me to emphasize that it's a general setting from what we had before. So now we look at the P sum with respect to a symplectic splitting, not with respect to a Lagrangian splitting. Okay, and this is a joint project with Pazit Chaim Kislev, who's a student of mine, and in this case, we consider first the well-known symplectic invariant, which in the case of convex domains, it's called the Eckland-Hofer-Zender capacity, which is just the minimal action among closed characteristics on the boundary. Now I should say here that K and T should be convex. I'm only thinking about convex domains. So we can prove that we can generalize the product property from the case P equals infinity, which corresponds to the product of two convex bodies, to the entire family of P sums. So note, it's kind of maybe surprising that for P, all the way between 2 and infinity, we get the same answer as we get for we always get the minimum of these two capacities. Now there is one claim which is trivial because the 2 sum is a subset of the product. So it's definitely less than this minimum, but it's a priori surprising that it is at least the minimum. And the 2 sum of these convex bodies is a smaller subset than the product. Okay, and we have this kind of strange average of the 2 capacities for P between 1 and 2. Okay. Any questions about the statement? Okay, so I can make maybe one more comment about the P sum of convex domains, and now I want to focus only on convex and concave toric domains, but not necessarily in R2. And there is a family of symplectic invariants constructed by Gut and Hutchings using S1 equivariant symplectic homology. So this is an infinite sequence of symplectic capacities. I'm going to refer to these capacities as the Gut-Hutchings capacities. And in the same paper, Gut and Hutchings explained how to compute these capacities for convex and concave toric domains. And if I understand correctly, these capacities, at least in the class of convex domains, are conjectured to coincide with the Eckland-Hofer capacities. I'm not sure if this is known or not. But for convex toric domains, Gut and Hutchings gave a formula to compute these invariants based on the, say, combinatorics and geometry of the toric image of the domain. So you don't have to completely to consider precisely the formula. The point is that for convex or concave toric domains, there is more or less a precise way to compute these symplectic invariants. And kind of an observation that more or less follows immediately from these formulas. So I wrote down the formula in the case of convex toric domain, but there is a similar formula for the concave case. And here we can also generalize the behavior of this product to the case of the P sum of 2 toric domains. But for some technical reasons, we believe that the formula should be hold in a more general, I mean, in the toric picture, but maybe without such restrictions of convexity or not. But currently, we can prove these formulas, say, for convex toric domains only for values P which are greater than 2. And in the other case, where we consider concave toric domains, we have to restrict ourselves to the case P between 1 and 2. So this what follows more or less immediately from the formulas, but we suspect that this should be true in general. So both for convex and concave toric domains. The formula should be true for arbitrary toric domains without this assumption of being convex. Any questions before we move on? Okay. So now let me go back and try to justify why, in the case of the Lagrangian splitting or the Lagrangian sum, there is a priori hope to be able to say something about symplectic embeddings. So I'm going to maybe skip, let's say, I'm going to skip some slides here. Maybe I will go back to them. But let me say a few words about going back to the symplectic inner and outer radii of these configurations of Lagrangian splitting. So what I would like to convince you is that from the Hamiltonian dynamics point of view, this splitting, say at least in the case where p equals infinity, has a very clear and precise Hamiltonian dynamics interpretation. So now I'm looking at the case p equals infinity, so just the Lagrangian product of two convex domains. And we want to say something about the rep dynamics on the boundary of this domain. And the interpretation of the rep dynamics on the boundary is, or can be interpreted as a Finsler billiard dynamics. So at least in the case of p equals infinity, when we take the actual product of two convex domains with respect to this Lagrangian splitting, we have a very precise Hamiltonian dynamical system, which is to play billiard in one of these domains with respect to the geometry that is induced by the other domain. So what do I mean by that? We look at the Hamiltonian function that gives us this Lagrangian product and the corresponding vector field, and we can follow the dynamics. Say, suppose we start at, say, a point here and here. So a point on the interior of K and on the boundary of the other domain. Then the rep dynamics, so the direction that we need to move, is determined by the outer normal at this point. So the dynamics is to move in a straight line till we hit the second point here, denoted by Q2. And then, of course, we arrive to kind of the singular strata of the energy surface, right? The product of the two boundaries. So here, a priori, the dynamics is not well defined. Right? We cannot, I mean, it's manifold with corners, right? We have the product of two convex domains. And the magic here is that under convexity assumption, say in the case where both K and T are strictly smooth convex domains, then there is a natural way to continue these dynamics. So even though it's kind of a singular, we are in the singular strata, there is still a way to continue the dynamics so that now we look at the outer normal at this point, and we start to move in minus this direction in the other domain till we reach this point here. So we basically go in and out the singular strata every time, but the dynamics can be, again, if K and T are smooth and convex, let's say strictly smooth and convex, then one can extend this dynamic to the singular strata. And when we project everything, say, to the X space or the Q space, we have a billiard type dynamics inside K. But this dynamic is not the usual billiard. We don't have the usual reflection law. We have a billiard dynamics with respect to the geometry. So this is the billiard table, and this is the geometry with respect to which we play the billiard game. So my point is that, at least in the case p equals infinity, we have more or less reasonable understanding of the Reb dynamics on the boundary. And in many cases, we can actually compute, say, what is the minimal orbit, especially if we have some additional symmetry assumption on the body k and t.
Sorry, is there some foliation, or in this case, or are you in the case where you have several characteristics which can collapse at some point, or?
Yes. So I mean, away from the singular strata, you have no problem. You have a well-defined dynamics.
Sure.
And in the singular strata, without assuming anything, there is just no way that you can extend the dynamics to the singular strata. And the point is that under these convexity assumptions, so say smooth, convex, and strictly convex, there is a unique way to extend the dynamics to get this billiard that we have in this picture. So maybe you can think about the example where, without, when you just assume convexity, you can think about something like a hypercube in R4. And here, even though that you have convexity in, say, these parts of the singular strata, there is no unique way that you can extend the dynamics. But if you have kind of, in addition to convexity, also strict convexity and, say, smoothness, then there is a unique way to extend the dynamics throughout the singular strata. Okay, so what we see from this picture is that, at least in the case p equals infinity, when we look at the Lagrangian product of two convex configurations, then this system, this Hamiltonian dynamical system, has a very natural interpretation. Just linear dynamics in one of the domains with respect to the geometry induced by the other domain. And it's still not completely clear, even though we do have some insights into this question, what is the interpretation of the two-sum, the Hamiltonian dynamical interpretation of the two-sum of two convex domains with respect to this Lagrangian splitting. But at least for p equals infinity, this class is very natural. So now I'm kind of going back to the beginning of my talk and justifying why I want to suggest this particular class of convex domains. So again, at least in the case of the Lagrangian products, we have some control on the Reb dynamics on the boundary. We have some tools that we can use to gain some geometric understanding of the Reb dynamics. There is another story which is related to what Kai asked me before about a very special configuration of the convex body times its dual, which is kind of related to a 80 years old open conjecture in convex geometry, which is known as Mother conjecture. But this is, I see that I'm running out of time, so this is definitely a story for a different lecture. So let me stop here, and thank you very much for listening.
Thank you. Is there any questions?
So for instance, if P and Q are different, but in the same range, say between 2 and 9/2, can anything be said?
You mean in the first, I mean, for the Lagrangian product of two disks?
Yes.
So let me just go back to the formulas. Sorry. So I'm not completely sure if I understand the question. Are you referring to
put different norms, but take P and Q in kind of a same range?
Oh, you mean instead of taking, say, x to the p, y to the p, take x to the p, y to the q? And
right.
Yeah, that's an interesting question. We didn't try to do this computation. Yeah, it's I don't know the answer, but it seems reasonable that at least in the case of these two disks, there is some hope to be able to answer this question.
I think it's going to be a toric domain as well. We could find another curve. It's going to be more complicated, but I think it's possible to compute that.
Mm-hmm. Yeah, I should say that it's a kind of a general interesting question to ask when a convex domain has this toric, say, the interior is symplectomorphic to a toric domain, and then we can try to attack this question.
Yaron, you say that when P is bigger than 9/2, it's a complicated function of P. Do you have any clue? Do you have any idea about what this function is?
Oh yes, I mean it's a. I mean there is some unpleasant integral that needs to be written down, and then you have to take some derivatives of this integral as a function of P, and yeah, I mean we can write it down precisely. Just don't have enough, enough space on the slides to write it down precisely. But yes, I mean we know precisely how. I mean there is a closed. In some sense, we have a formula for.
Does it exhibit a sort of staircase? I mean, does it have sharp corners, or is it sort of just smooth in some way?
No, I want to say that it is smooth, but I don't know, Vinicius, do you agree?
Yes, I think it's smooth. It's something implicit, we don't have a nice expression, and we just have to use inverse functions of integrals that we can't solve.
Right.
That's why it's complicated, but yeah, it's smooth. It's a smooth function of P.
Right.
Can you say a word on the proof of the result for the symplectic product?
Yeah.
What kind of tool?
Here, so let me. Sorry about changing. You mean here for this statement?
Mm-hmm.
Yeah. So it's it uses the fact that in this convex configuration we have Clark's dual action principle that one can use to to compute the closed characteristics with minimal action, and based on this relation, one can compute this formula. So it's some analysis of the Clark's dual action formula for the minimal action on the boundary of the convex domain.
Okay. Thanks.
Yeah, maybe I should make one more comment that. Say here, so for example, maybe this is not very impressive, but as I said before, ellipsoids are the two sum of ellipsoids. So in particular, we can recover, say, the formula for the good Hutching capacities in the case of ellipsoids, because we can decompose an ellipsoid into the two sum of ellipsoids all the way to dimension 2. And using this formula, you immediately get a result which was known before, follows from the previous formula, computing these capacities, say, in the case of ellipsoids. Convex domains for which the answer is known. For the volume capacity conjecture, there are some classes, but usually they require some sort of symmetries, like say some S1 symmetry or some. But other than some very special cases,
yeah, okay.
Still, yeah, the general question is still open.
Can I ask you? Sorry.
Okay. Please.
Yeah, maybe I have a question in the same direction, but it's not exactly related to the talk either. More. So I'm a PhD in convex geometry, so I read about this work. And I was wondering, like, I thought you proved a Brand-Minkowski type inequality for the Eckland-Hofer-Zehnder capacity. So if the strong Viterbo conjecture is true, there should be the same inequality for any capacity, right? So I was wondering, like, is there some, I don't know, some work to try to see if it holds for the I don't know, say the cylindrical capacity or the Gromov radius or stuff like that, like geometric capacities like this?
Yeah, unfortunately, I have to say that the Gromov width seems to be completely out of reach for these type of questions. I mean, seems to be very difficult to say something about the behavior of the Gromov width. For the cylindrical capacity, it's slightly a different story, because we are somehow getting more and more evidence that, well, of course, we still don't know that the cylindrical capacity is coincide with the minimal action, but we already know that they cannot be too far away from each other. So they are bounded by, I don't remember, 4 or 2 or some constant. So I don't know if I'm not aware of any work in this direction, but if I had to guess, I would start with the cylindrical capacity and not with the Gromov width. Somehow seems more difficult to approach.
Okay.
And I have also some, I mean, slightly further off question is, you have this inner radius and this outer radius. So you have basically, if you compose, you have like a symplectomorphism. Oh, it's a ball in the ball in the ball. Yeah, so it will always be equivalent to the inclusion. Oh, okay. No, I was yeah. Okay. Then no question. I was curious, like if you change like the ball, or if you take some ellipsoids, radii are near, but if you add like a knottedness condition, does like suddenly the ratio of the bound increase? But it doesn't make sense.
I can use this opportunity to ask you a question about capacities. So, do I understand correctly that in general, without this toric convexity / concavity assumption, it is not clear whether you have the product formula for the For the capacities?
I want to say we believe, but since Michael is not there to correct me, let's say I believe that yes, we still have the product property in general, but I mean we thought about how to prove it, and it was completely unclear. I mean, basically, if you want to prove it in general, you need kind of a product structure on the positive S1 equivalent symplectic homology. And that seemed not so trivial to do. I mean, we tried a bit, and it was not so nice to do the product which would get exactly what. I mean, we are still thinking about it sometimes. So.
But when you say product property, you mean product for the S1 equivariant capacities, right?
Yeah, just this formula that CK of X times Y is like say.
Sorry. I was thinking about something else. Yes, no. This yes, this one should be. So
this should be true. That without.
Yes.
Without the convexity, okay.
Yeah, like the same product formula as Klemford-Lanhofer capacities.
Okay.
Yeah. This one should be true. Yes.
But do you know if it is written somewhere or just?
It's under progress, but we are moving very slow at it. So yes, in the next 10 years it should appear somewhere. No, but it should be true. I mean, I can say more, but it's.
Hi, Yaron. I have a question. I don't know if you can hear me.
Yeah, I can hear you perfectly well. Hello.
Thanks for the nice talk, anyway.
Thank you very much.
I haven't figured. I mean, I don't know. Do you have a bounded ratio between the inner and outer balls in the case you consider?
In the P sum of two disks?
Yes, well, for example, for the P sum of two disks.
Yeah, I believe here, yes. But in general, I mean, even for ellipsoids.
No, in general, of course not.
Yeah, but.
Could you improve that if you replace balls by ellipsoid? A little bit in the idea of the John ellipsoid.
Oh.
Trying to so of course I would put the capacity of the sets. So if you put an ellipsoid inside and try to have an ellipsoid containing the set, is the ratio of the capacities bounded somehow, or at least for a reasonably large class of set by something better than the John. I mean.
Mm-hmm. Yeah, I mean, I try to think about kind of what is the analog of the John ellipsoid in the symplectic setting, and I have to say that I don't have a good answer to this question. So one can rephrase this question in say, if you fix the volume, you can ask what is the linear image of the domain that will maximize, say, the minimal action. And even for the cube, it's not completely clear.
I see.
So yeah, I think that it's kind of it's a very interesting question, but I mean, we can. If we have enough symmetry, we can say something about it, but in general, I really don't know what the answer should be. What is kind of the analog of the John theorem in the symplectic setting.
Okay, thanks.
I was thinking that if you allow yourself to go to ellipsoids rather than just only balls, then you will also finally find the staircases that Dusa was asking about.
Yes.
Yeah, I mean, the the P sum of disk is really only one example. One can, of course, consider many other configurations.
Yes.
But for example, even in simple examples like so the two sum with respect to a Lagrangian splitting of a square and say the L infinity and the L1. So this is something that I believe that one can do in some sense using Ramos and Sepe work. And I think this is somehow approachable, but or even P, but in general not completely clear. How to control the dynamics of these configurations.
And also, I remember in Haifa, I'm sorry, I have a problem with names, so I cannot remember her name. But there was
Bazit Chaim Kislev, the student I mentioned before.
Yes, I think that's her.
Mm-hmm.
So she was doing computation for polyhedric domain, as far as I remember.
Right. Mm-hmm. Mm-hmm.
And I had the impression that this could help with this kind of problem. Did this lead somewhere in this direction, or?
So,
yeah, you mentioned her name. I somehow didn't.
Yes. Yeah. Let me write it down. Bazit Chaim Kislev. Yeah, so she really studying kind of the Reb dynamics on Reb dynamics on convex polytopes.
It looked very explicit, which maybe it was not as explicit as it looked in a way, but
I mean, she can write down a formula. It's kind of amazing that it's a very precise formula, but
yes.
Now it boils down to combinatorics, but it's a very complicated combinatorics. So it's a mixture between combinatorics and geometry. And I should say that even for relatively simple classes of these polyhedras, like simplices, for example, other than maybe R4, R5, R6, R8, in arbitrary dimension, it's a nightmare to do the combinatorics and see, say, if you can prove the volume capacity conjecture. So we have a formula, but so now it boils down to some geometry combinatorics problem, but seems to be very hard to solve.
Okay. Thanks.
Yeah.
Maybe I can bother you with another question. So, you know, I liked a lot the way you presented the fact that when you do, I don't remember which sum, it looked like you were playing billiards in a convex polygon with the geometry being controlled by a different polygon. Like,
right.
I don't know, something like a Finsler metric, but not really. Yeah. And I was wondering how your story today connects to the story of K area yesterday. Right? Because you are, I mean, of course, say it's convex with smooth boundary, right? You are kind of considering some unit, you know, cotangent bundle of that object.
Right.
Yeah, but I'm not sure exactly what the metric is or whatever. But
no, I mean what you said is this is exactly this, right? I mean in the Lagrangian product, this is really the unit cotangent bundle, right? You have one domain which is the kind of the table, the billiard table, and the other domain is the norm on every fiber, which gives you the geometry.
Yeah. But this would be the case in the infinity.
Right, and not when you start to change P, right?
Not when you start to change P. When you start to change P, something funny happens. I mean, it shrinks towards the boundary. I don't know.
Right. Yeah. This is kind of the main thing that kind of we would like to understand what happens to the dynamics. So you have this very clear interpretation of billiard dynamics in the case p equals infinity.
Yes.
And now, as you said, it becomes an interesting question. What happens when you start to change p? Do you completely lose control, or do you can still trace trace the orbits in some way?
I have a kind of follow-up question on that. If you consider a billiard where, let's say, the base has corners, but the fiber does not have corners. Okay, so so it's, for example, the standard metric. People doing billiard, they usually disqualify closed trajectory that would hit the corners.
Right.
Is there any red dynamic reason for that? Because I always had the impression that this was artificial and that there was no reason to exclude trajectories touching a corner, except that it's, I mean, they consider it's ugly or something. But
no, I mean, I agree that from the rep dynamics point of view, it makes sense to consider the orbits through the singular strata. But I think the problem is that, so convexity essentially tells you, you have, instead of an ODE, you have this, differential inclusion, right? The gradient is in this cone of vectors.
No, what I meant is that could there be that if you go through a corner, the Kohn-Lesender index becomes too large, and so that,
I see.
And so that you can say that the orbit is not going to be minimizing in some way, or is there this kind of?
Yeah, that's a fantastic question. I'll be very happy to know if from this point of view, indeed. But somehow I think
you can approximate the corner by rounding it off, and
you can do, of course.
And if you do that in the approximation, you can probably control the Kohn-Lesender index. Right.
But can you?
They're all gone, so I can remove.
Maybe for the minimal one, so that there is.
No, maybe what I mean is maybe going through the corner prevents you from being minimal. But I don't see.
But I mean, in an obtuse triangle, right? I mean, it's the minimal one.
Yes, I can go through the. So I don't.
It's the high.
No, so it's probably probably what I said doesn't make any sense. Probably make sense. But I still don't understand why these people exclude the
corners.
The corners in their point of view.
If you do ergodic theory, it's fine.
It's because it's very hard to find orbits that don't go through the corners, like for triangles.
You mean otherwise the problem would be too easy, so make it more difficult?
For triangles, if you smooth the corners, there are plenty of billiard trajectories, periodic billiard trajectories.